Hello folks, so today we're looking at contingency tables and we're going to use the chi-squared test, which hopefully you remember from the goodness of fit tests. We're going to use that to test contingency tables for independence. So what is a contingency table? Well, you'll probably know it better just as a two-way table that you met at GCSE, and these sorts of questions offered a good easy few marks in GCSE papers, so just have a go, pause the video, see if you can fill in the missing values on your sheet. Okay, so hopefully you got these values, which are nice and easy to get just through using a bit of adding and subtracting, and it says here that these are the results for a school's Year 11 Maths GCSE students, and it must be from a couple of years ago, seeing as they're still letters. So a question that we might obviously ask is, does gender affect the likelihood of gaining a grade C or higher in maths? So we can just look at the table to make some inferences on that. So we can see that in total just under half the students were boys, so we would expect therefore that just under half of these A star to C grades would be boys. Well, you can see 90 is just under half of 186, so that looks about right. And similarly we would expect just under half of these D to U grades to be boys. Well, in fact there's 40 boys, is in fact just over half, so perhaps there's a few more observed values here for boys with a D to U than the expected result that we'd get. So what we're always thinking about is the proportions of these totals from the grand total here. Okay, what's another way of asking this same question? Well, we could think about the opposite, and the opposite would be that the grade here is independent of the gender. So what we tend to do is actually make an assumption that these things are independent, and then we do a hypothesis test on that. So let's have a look at the principles. It says if the variables are independent, then we would expect the proportion for each section, in this case the grades, of each variable to be about the same as the totals proportion. So in other words, looking at this, the proportion of boys getting an A star to C would be about the same as the total proportion of boys. Okay. We produce expected values using the totals proportions, and there's a really nice easy way to do that. We then compare the expected values with the observed values that we've got. If they're similar, then we can assume independence. If not, then we suggest that they're not independent. So an example here that you've got on your sheet, it says a biology student observed snails on a limestone pavement and in a limestone woodland. The colour of each snail was recorded. Does the ground type impact the colour of snail found? Okay, so we've got here a two-way table, the two ground types, three different colours. We've got 6 pieces of observed data there, and it's nice and easy for us to get these totals. And also easy for us to check these totals, because obviously these two should add up to 65, these should add up to the same. Okay, it's a hypothesis test, so we need our hypotheses. Our null hypothesis is that they are independent, so we assume independence, and then the alternative will be that they're not independent. You could say that colour is dependent of ground type, but we do tend to say not independent. We need to get the expected values for each of these. Okay, and the expected value can be found using this formula here. It's the total of the row multiplied by the total of the column divided by the grand total. So for this one here, for pavement light, it would be 35 multiplied by 30 all divided by 65. Okay, and if you work that out, it comes out to be 16.15. And then for this one here, the medium on a pavement, again it would be 35 multiplied by 20 divided by 65. And you can go through and work out the expected value for each one. Then the test statistic is exactly the same as that used for goodness of fit tests. So we do the difference between O and E, all squared over E. So for the first one, difference between these two, square it and divide by E, divide by 16.15, and we get this value here. And again, we can work out that for each of our 6 cells. Some people prefer to put the expected values up here in the table itself, and others prefer to do a whole new table. I would suggest whichever method you're going to use, you need to make sure you write down these values. Alright. The test statistic tells us, or the formula tells us, to find the sum of those, so we can add them up and we get 11.6 in this case. So that is our test statistic. We know that we need our critical region, so our critical value, our chi-squared value here, and we were asked to test at the 5% level, so our critical region needs to have 5% at the top end here. Alright, we know that we need the degrees of freedom, and the degrees of freedom, if you remember from the goodness of fit tests, is thinking about how many observed values can vary. So here we've got 6 values, but if we knew that this total was 35, then once these two were in place, then this one would be set in stone. And also if we knew that this total was 30, then once that one's in place, this one would be set in stone. And similarly for this one. So in fact, in this table there are only 2 values that can vary if we know the totals around the outside. Okay, so the degrees of freedom will be 2, and we can generalize that for different tables. There'll always be one column that is set in stone, and there'll always be one row that is set in stone. So to find the degrees of freedom, it's always the number of rows minus 1 multiplied by the number of columns minus 1. So in this case it's 2 degrees of freedom. Okay, so we can look that up in our chi-squared table. So if we just go to the table, we've got 2 degrees of freedom. We want 5% to the right, so 0.050 to the right gives us a chi-squared value there, a critical value of 5.991. So there's our critical value. We then compare our test statistic to that, and we can see that 11.6 would be up here in our critical region. It's greater than our critical value, so hence we reject the null hypothesis. And in the context of the question, we can say that ground type does affect colour. Alright, or we could say there is evidence that colour and ground type are not independent. So there's a question here for you to try that you've got on your sheet. So you'll need to put some totals column and row along, but have a go, pause the video, and then you can have a look at the solution. Okay, so for this one, null hypothesis and alternative hypothesis are similar to before. As always, the null hypothesis is that they are independent. We can work out our expected values in the same way, which was total column times total row over the grand total for each one. Should get those values there, and we can add those up to get our test statistic. The degrees of freedom this time, 4 columns, 2 rows, so 4 minus 1 times 2 minus 1 gives us 3. The critical value, 5% to the right with 3 degrees of freedom, is 7.815. Our test statistic has come out to be 8.08. And we can see that that is greater than the critical value, hence it has fallen in the critical region. There is evidence to reject the null hypothesis. Results are not independent of school. Okay. So which school has the better results? We could continue the question a bit. Well, for this really we need to compare the observed values with the expected values, and hopefully you can see, as it says here, Kingswood has lower than expected numbers of top grades. So if we look at this one, it's got 8 grades A to B. We would expect nearly 14. Okay, it's also got higher than expected numbers of lower grades. Sorry, this should be higher here. Down here, both of these are higher than what we would expect. Okay, and conversely, Queenswood has got higher than expected at the top grades, and it's got lower than expected at the bottom grades. So hence we would say that Queenswood has the better results. Give 2 reasons why the school with the better results may not be the better school. Well, firstly, this is only looking at a single subject. It was looking at A-level maths, obviously a very important subject, but a single subject nonetheless. And also we should consider the varying levels of ability of students entering different schools, and if that differs, then the expected results would differ. Okay, so that is contingency tables. Hopefully that's given you a clear introduction, and you can ask me about anything you need to in the next lesson. Okay, thanks, bye bye.